Assalamualaikum and hello everyone. Both CEB1063 Process Heat Transfer and CEB1072 Chemical Engineering Thermodynamics 1 have integrated the syllabus to ensure the students manage to relate the theoretical concept into the real life situations. In this integrated project, combined gas steam power cycle plant is proposed to be built in Lumut Perak for domestic usage and the new Lumut Naval Base, which is aimed to produce 500 megawatt of electricity. The proposed power plant must follow these specifications given, which inlet steam temperature up to 700 degrees Celsius with pressure up to 30 megapascal and utilizing Turbo Camprowaja TRL-12, a 50 megawatt high technology steam turbine to generate electricity which utilizes water as the cooling medium economically and ecologically efficient. Both over efficient and BWR back work ratio of the combined gas steam power plant that will be built are determined with further aspects being elaborated in the discussion part.
Next, there are some assumptions made in the proposed design. Firstly, all equipment used is steady flow devices, which means that there is no change in the energy and the mass flow rate will always remain constant. Then the kinetic energy and potential energy are negligible in the process. Also, there is no pressure change in the combustion chamber and condenser, as well as no work interaction in the combustion chamber, heat exchanger and condenser. The turbines, compressor and pump are all well insulated and internally reversible. The pipe is assumed to be frictionless and no leakage between the pipelines. Moreover, the compressor and pump are assumed to be adiabatic, so no heat will lost to the surroundings. The last assumption will be the air and water as an ideal gas and incompressible substance, respectively. The picture here is the schematic diagram of our design. We have 3 gas turbines in the gas cycle and 3 steam turbines in the steam cycle, in which they are all split and combined by the splitter and mixer with the flow ratio of 1:3. We also assume the feed mass flow rate of air and water. Now we zoom into the gas cycle. For the air in, the temperature and pressure are assumed based on the ambient conditions of air in Malaysia. Then, as the air is compressed in the compressor's outlet temperature, which is the inlet temperature of the combustion chamber, should be higher than 37 degrees Celsius. So we assume it as 500 degrees Celsius. After that, the air is heated in the combustion chamber, so we assume it to have an outlet temperature of 1600 degrees Celsius. Moreover, we also assume the air pressure after exiting the gas turbine to be 101.3 kilopascal, which is the same as the air pressure. Next, we move to steam cycle. For the turbines, we assume their inlet temperature and pressure as 600 degrees Celsius and 12.5 megapascal respectively according to the question. Then for the condenser, we assume no pressure change and its inlet stream will be in the saturated liquid vapor mixture state, while the outlet stream will be in the saturated liquid state. Moreover, we also assume constant pressure in the heat exchanger. In this project, we use Aspen-Hythe simulation to calculate the values. Hence, in order to prove the values, we use the energy balance equation to determine the ideal value. This is the manual calculation for compressor. After we obtain the ideal value, it is compared with the value from the simulation by calculating the percentage error. The table shows that the percentage error of each equipment is lower than 10%, which indicates that the values from the simulation are reliable and accurate. Next, the amount of coal required is calculated, in which the type of coal used is anthracite with the heating value of 30080 kJ per kilogram. The calculated amount per second is 33.9742 kg. Then for the steam generator, we use the outlet stream of the heat exchanger in the steam cycle to determine it. The amount of steam generated is equal to 15737.905 meter cube per hour. For the actual power produced, we can calculate it by assuming the values obtained from Aspen-Hythe simulation as actual condition. The actual power is the net work done by the circle. Hence, by using the work done by the gas and steam turbines to minus the work done on the compressor and pump, we can know the actual power produced equals to 500.114 megawatt, which is slightly higher than the required power output of 500 megawatt. Then, for the overall efficiency, it is calculated by dividing the net work with the heat absorbed by the combustion chamber. Next, the backwork ratio for the gas and steam cycles as well as the combined gas steam power cycle are calculated. The backwork ratio, which is the ratio of the work done by the turbines to the work done on the compressor and pump, is a way to analyze the performance of the equipment. The calculated values are all met the range of ideal values, so the power plant can be said that it is operating at a good performance.
The proposed design solution is the combination of Brayton cycle and Rankine cycle. So what is Brayton cycle? Brayton cycle is a gas cycle which extracts energy from flowing air. This includes a few processes which are adiabatic compression of air through compressor, constant pressure heat addition through combustion chamber, adiabatic expansion of gas turbine, and lastly constant pressure heat rejection by condenser. Rankine cycle or steam cycle involve a few processes which are isentropic compression of pump, constant pressure heat transfer through heat exchanger, isentropic compression of steam turbine, and lastly constant pressure heat rejection of condenser. The inlet of the steam turbine must be in superheated steam to prevent from erosion, and the inlet of pump must be in fluid to maximize its efficiency. The proposed design is also based on a few important thermodynamics laws and concepts. Firstly, first law of thermodynamics. The first law stated that energy cannot be created nor destroyed but can be transformed from one form to another. This is done as the heat supply to combustion chamber is converted to work and then used as the power generation for electricity. Next, second law of thermodynamics. The second law stated that due to increase in entropy, heat cannot be converted to work without wasting some heat. Heat is wasted as the energy is transformed and transferred, which causes the efficiency of the cycle to be lower than 100%. Other than that, ideal gas behavior. Ideal gas behavior is obtained when the highest pressure in gas cycle is lower than the critical pressure of air, which is 3.77 megapascal. The thermodynamic concept also involves ideal cycle. The design is assumed to follow ideal cycle to get the maximum efficiency possible. Although the highest efficiency can be obtained through Carnot cycle, it is not practical to be used due to its isothermal processes. To get ideal cycle, a few assumptions are made. Firstly, no friction involved. Second, pump, compressor, and turbine must be in quasi-equilibrium process. Lastly, connecting pipe must be well insulated. The last concept is steady flow device. The energy change of steady flow device is equal to 0. That's why energy in is equal to energy out. The kinetic and potential energy is assumed to be negligible. Thus, the final energy balance is as follows.
The proposed design is done by applying concept of Rankine and Brayton cycle. All percentage errors are lower than 10%, which indicates that the value from Aspen HYSYS are reliable and accurate. Since turbines are used in the combined gas steam power cycle and the actual power output is 500.114 MW, which is slightly higher than the required power output. Recommendations are made to improve the efficiency of the overall combined gas steam cycle. To begin, a well-insulated pipe is the best design because it can prevent heat loss to the environment while producing more power. Besides superheating the steam to high temperatures, it will increase the network and heat input. It also reduces the moisture content of the steam at the turbine output, thus the mass efficiency is increased due to the average temperature as more heat is transferred to the working fluid in combustion chamber. Thus, the charcoal could be replaced with natural gas as a fuel source because it is easy to control the burning rate of natural gas by adjusting the fuel to air ratio. As a result, the fuel to air ratio approaches stoichiometry and increasing burning efficiency.